Okay, so to understand what I do a little better, I will just give you a brief background in what I do in my research. And as Prasad said already, my research is about doing what we have for the mobile phones, namely an app economy, where we can install apps on our smartphones and use them to implement that also for pervasive computing, namely for smart spaces. And that means that we could install apps in this room, for instance, that are controlling the functionality here, like the lighting. So that we can just say, okay, now we have this presentation and we have the presentation app, and then it's just running that one. Okay, so to get a little bit more into detail, for enabling such an app economy for smart spaces, I look at different things. For instance, I look at service management, also an app store. I look at user interfaces, so how can you control all those things? I look at smart device gateways, so how can you interface those tiny devices that do the functionality in the end? And in the core, I also look at a programming abstraction or an operating system that you need in order to run such an app economy for the smart spaces. And what I will propose or present to you today is a follow-up from my presentation at NOMS last year. And the abstraction I use there is based on data models, as you know it from when you are familiar with element management. And another important aspect, of course, is also security, but in today's talk I will focus on the programming abstraction that we have down here. Okay, so more in particular, what will I look at? So I will look at what is a suitable programming abstraction for pervasive computing, or to put it into other terms, also the same question would be, what is a suitable operating system for the Internet of Things? And this is also exactly where big data and network management, element management comes in, because all those tiny devices produce lots of data. And I tell you how it could be possible to manage such data in a distributed way. And in this talk I will show you how methodology from element management can be of help when answering the question what could be a suitable operating system. Okay, so when we look at the problem space, what I basically want to do is something which I call smart space orchestration. So what I want to do is I want to have some software here, some apps that have a manager role, so they do something while connecting some other software that is then interfacing some devices. So in management terminology, they are typically called managers because they implement some high-level goals. Those are called agents because they provide access to the smart devices, and then we have the managed devices. When we look at element management, tasks that we want to do is like we want to provide telephony, we want to provide best data throughput, whatever. When we look at pervasive computing or Internet of Things, what we want to do is we want to interact with the real world. So we want to control, for instance, the lamps here, or we want to measure how bright it is in here, how many people are in here. So you see already that the field of what those devices do is quite broad. Okay, so who's managing that stuff? So in the end, there are still some users that say like, okay, I want to feel good in here, for instance, and then the system has to do something. And they communicate with the managers via user interfaces, and there again the cell phone comes in, the mobile phone. So you could just use your mobile phone, for instance, to do something, or you could speak, or whatever you can imagine as user interface for such a space. Okay, so basically then I say, okay, I want to feel good. I tell it to my interface. The interface is connected to a service. The service has some logic that knows what does it mean when I want to feel good. Contacts then different services that can do something with the environment. And then in the end, the devices are reconfigured, and then the reality is changed, and hopefully I feel better than afterwards. The problem now is, which I look at, these middle layers here, because this is the software, because apps are software, and so creating software for such purposes is quite complex. And why is this the case? The basic case is what I've written here. The case is heterogeneity. So we have heterogeneous interfaces because of different reasons. We also have different locations where the devices are. When you imagine you would control this room, you would probably have some room controllers there, then you have maybe some sensors here and here. And when you want to write software that connects to all of them, you have to do that. And that makes the software complex. Then we have different vendors. So even if you have the same functionality, different vendors aim to provide different interfaces to save their market shares. And you have sensors and actuators for different purposes. Because when you think about smart spaces, you have something like medical devices could be interesting, entertainment devices, security devices. So you have a really broad range of things. And when you want to create now software that controls all this, the good message is it's possible, you can do it today. the bad message is this software gets quite huge. So you have to program lots of lines of code, and you also have severe problems when it comes to an app economy, because this software is most likely not portable at all. Because you will program it against some certain sensors, and it will work with those sensors and actuators, but it will not work. For instance, when I created it for my space, it will not work in preset space, for instance. This is a big problem. Okay, so what can we do? Something that we can just introduce from a software design point of view is we introduce middleware. And the purpose, or first, what is middleware? So when you have a single system, then middleware is of little use. There you have an operating system that provides an abstraction with transparency to the hardware and the things you have in the computer. When you have a distributed system, then you talk not about an operating system, but you talk more about a middleware, because it provides a unified system view to a distributed system. And so this is exactly what we need here, because we have some distributed things. So it can provide location transparency, and it can also provide interface unification, so that will lead to access transparency, which are two major things that are important here. Okay, so that means with a middleware, I will show in the talk how a middleware could be designed that provides that. With a middleware, we can already facilitate and structure the task of creating those apps. And when analyzing what else could help those app developers so that it gets as easy as it is for mobile phones to develop apps today, to develop apps for smart spaces, I also found out, okay, so a general task that you have to do when you want to create those apps is you have to manage data somehow. You have to move data from A to B, and you have to manage your own data. Like when I tell my service I want to feel good, it has to store somewhere that I really want to feel good. And this is why in my middleware, the middleware also provides data management capabilities here. So that means a service connects to the middleware and can then use the middleware as storage for data and also as broker for data. Okay, so when we look at this picture, you might have noticed that these planes got colored right now. The reason is that they are pairwise connected. So outside you have the real world, then you have the computer interfaces, so the smart devices that do something. And in the middle we have the software world, or also called the virtual world, where the software is residing. And having this picture, we can just restructure those 7 planes so that we have only 4. This happens like that. So now we only have software. We have the middleware as operating system here. This middleware I call virtual state layer, because it's managing the virtual state, which is a reflection of the state of the physical world that we have around here. Okay, and then below that we have the devices that interface in the real world, because they're user interfaces or they're sensing or actuating something within our spaces here. And so now we have some data-centric abstraction in here, and that is used to couple services. So let's have a closer look at that one. So we have a software, and each software is associated with the data structure. And you can imagine this data structure just like a tree. So if you're familiar with the SNMP protocol, for instance, for network element management, there you have a tree that contains some management information. And this is a very similar concept here. So here you have a tree, and here you have properties. So this one here could, for instance, be the room temperature. And if you have a second service, the same concept. So you have a middleware component that is managing this state here, this data. And when this service wants to access now a node on the other side, for instance, it can just do so, via a normal get and set operation. Okay. Now what we want to do is we want to couple services there. So this one is just generative coupling. So someone provides some information and someone else does time-space decoupled retrieve this information later. What we might want to have is some closer coupling. Okay, and the next coupling step is to have something that's called publish-subscribe mechanism. So you subscribe on changes on this node, and when the service on the right side changes the data in this node, you get notified, and then you can just query the information again. So this is then subscription notification. So there you have then asynchronous coupling. Okay, this is something that you know from network element management, probably because these concepts are known in SNMP, for instance. And what I want to do is I want to enable people to modularize the applications. And why do I want to do that? Because many applications have some common denominator. So healthcare applications might have something that all of them need, but entertainment applications might not need that functionality. And so it will be a good idea if you can just couple this functionality. So if you write a healthcare application, you can use the healthcare functionality, and if you use a entertainment application, you can use the entertainment capabilities. But at the same time, you still rely on the same mechanisms to be able to interchange information between the two worlds. And for that reason, I added a third mechanism, which I call virtual nodes. And this one is actually accessed the same way. But what happens, the data is not served by this database component, data management component here, but instead you have a callback inside the service, and this one is then generating the data and sending it back to the other service. Okay, so looking back at the big picture, what did we achieve so far? So we achieved, looking at the scenario from the beginning, the user can tell something to the user interface here, the corresponding service is then storing it here. Another service might do further processing with the data and set something here, and then this is the one that is controlling the smart device. It might see, because it subscribed itself on the node, for instance, okay, there's a change now, and then it might, for instance, switch on the light because it makes me feel better. And so this is what we achieved so far in here. So let's have a look at the mechanisms once again, because it's important to understand them. So now we again have these two services here, and I told you already we have 3 coupling modes. And this is the time sequence diagram we have here. So first we have the generative communication, so we just have a normal get, and we get a response or a normal set. And what is important to note here is that the communication ends in the middleware component here, so it's not ending up in the service. So this is a big advantage, because it means that if the service is going down for any reason, the data of it can still be available. And also the service programmer does not have to care about sharing the data with someone else, because the operating system here is taking care of that. So this is a great simplification. Next we can have the subscription. So here someone subscribed in a node here, then the data is stored there, and then as you expected, when the data is changed, you just get a notification. Okay, and the third mechanism is then the only one where the service is directly invoked here, and this is then the direct coupling. And here it's important that for the caller, it's totally transparent. So this is exactly the same as if you call a dynamic web page, because you do not see if it's a static web page or if it's a PHP generated web page, for instance. You just do the same call, you just call one URL. And so here's exactly the same. You call one URL and then you get data. And if it comes out of here or if it comes out of here, it's transparent for you. Meanwhile, this coupling mechanism here is much more powerful than this one, because here you can pass parameters and so on. I've written more details inside the paper. Okay, another thing is, this one here is managing state, while the application developer can just focus on the logic. And so this is also another big step. So you as application programmer can just focus on the logic of your software, and you can store everything you want in here. This makes your applications smaller and easier to read. Okay, so now some more interesting properties of this solution. So you all probably know about interface polymorphism, and using the model I was just presenting, we have some interesting properties, because what we can do is we can just hierarchically structure interface nestings. So that means if we want to extend this interface, we can just use the data structure inside our new data structure, and when services want to couple, they will just find each other based on these nestings here. Another interesting thing that emerges from there is that you can use the same interface multiple times. This is also something that you cannot do in a classic SOA, like web services, for instance, because the names of the functions would shadow each other. Okay, another thing you have from that, you have semantic polymorphism. That means if this service wants to access the data that is in here, but does not agree to the format because it does not understand it, you can simply, in this methodology, introduce some filter services, and then this one can access the violet service here because it knows the semantics of that service. Okay, more properties. We can do modularization right now. We have reuse. We can have some common functionality that we reuse. We have the separation of the logic and the state. We have unified access, and also very important, the interface modeling. So creating abstract interfaces became modeling data. So you do data modeling instead of interface modeling. So you do a descriptive task, which is easier for humans to grasp. Okay, then for those interfaces, for these models here, I introduced a central model repository, which is something like the ontology for a smart space in the end, which is created in a crowdsourced way. It allows reuse, and it also implements convergence support, which is important because you want to have portability. That means you want to have compatibility between services. More details about that in the paper from last year if you're interested. Okay, now I come to the end. So yeah, to check if this is a useful concept, I did a smaller user study with 8 pilot developers, which was conformed with more than 40 developers until now. So they had no big background in smart spaces, and to develop some core components, they found the task quite easy. This also reflects in the quantitative analysis. So here I just measured the time, a very conservative estimate. And so it took them between 4 and 8 hours to create some scenario like the one I was explaining before. And the only system that does comparable things that was evaluated like that, their comparable task took 256 hours, which is much more. So we see that the thing I was presenting seems quite intuitive to people. Okay, summing up, I introduced a data-centric, service-oriented architecture that seems simple to use because it uses descriptive concepts. It has versatile coupling via regular nodes, subscriptions, and virtual nodes. It's dynamically extensible with functionality. It has interface polymorphism beyond classic servers, including this 2-dimensional hierarchical interface polymorphism and semantic polymorphism. From a more abstract point of view, this is an extension to the Blackboard coupling packet pattern between services. And it's actually quite fun to use this abstraction. Okay, thank you. Comments and questions?
Thank you, speaker. We have time for 1 or 2 questions. If anybody has any questions.
You don't have to be shy. I know much more than I told you.
This is actually a pretty good session for the first session in the morning. I have one question. So the advantage is in the interface descriptions, right? The abstractions is the productivity you're seeing because of how you are managing the description, because the rest of the communication is sort of web services. So is the efficiency because you're able to more effectively describe the interfaces?
So let's just switch back. So the major differences for me to these normal interaction mechanisms is that more functionality moved inside the middleware. So this one is actually implemented as peer-to-peer system, where all these here are just can be one computing node, and this computing node is acting similar to like a distributed database. Mm-hmm. And so you have this distributed database plus exactly what you said. So you have the data structure, and this data structure is pre-known. So that means I have this ontology store there, and when I want to use a lamp, for instance, I can look it up at design time. How would a lamp look like? And at runtime, I can do a discovery, and then I will find all instances of this lamp inside these storages here, and then I can just connect there. And so this is a novel aspect, I would say. Yeah.
Question.
Yes, please.
Very interesting.
Thanks.
The middleware is an abstraction of the services that are on the layer. Is that what you said?
The middleware is acting as operating system that is used by the services on the upper layer.
Okay. Where do you do the abstraction?
The abstraction you mean, for instance, when I have a hardware device and I want to go to the virtual representation?
Yeah.
Okay, so it's a very good question. Yeah. So the abstraction is happening here by doing the following. So you have this device, so it could, for instance, be an Arduino device, which is interesting. And then you connect to here, and then here you have a service. And this service then has to know the semantics of this device, and it has to know how to transfer these semantics to the virtual representation it wants to use. Additionally, what is important, this component has to be autonomous. Because what you want to do, someone else says, I want to switch the lamp 5 on as this one is reachable here, and then it sets it here, and then this one has autonomously tried to reflect it down to the device.
So the abstraction is real time. You meant the devices are heterogeneous, right? Mm-hmm. And their functionality will vary with time as time goes by. Mm-hmm. So do you do the abstraction based on the functionality, or is it based on the components of the devices that you monitor?
Mm-hmm. So I would say both are highly connected because you have basically when you create the abstraction to such a device, what you will do is you will look at the device and then you will say, okay, it has 7 properties, and then you create a model that offers those 7 properties, and then you try to match the functionality. So it might be that you have to do some function calls to access this here. And then you match that one to the model here. And if someone changes the model, you do the respective calls. Concerning the extension you were talking about, what is happening in here is you can dynamically add new functionality, and this means that to this instance of these data models here, you just add new instances of data models. So you can say, okay, now I have a fridge or something, and then it's here. And interesting is if the fridge, for instance, contains a light, and you have a service that is shutting off all lights because it wants to save energy, and it uses the light model that was used by the service that saves energy, then it can retrieve it just using the ID of the other service. Right. Thank you very much for the question.